Let's spend a few minutes talking about Aryldiazonium ions, which are another way of substituting on aromatic rings. There are a number of groups X that we can use to substitute for this N2 group, and we would lose nitrogen gas in this step, which is a very favorable process. So the first question is really, how do I make this Aryldiazonium cation? We're going to start with aminobenzene, also known as aniline. We're going to mix that with sodium nitrite. And HCl, and that will produce the diazonium cation. And of course we'd have a counter ion there of a chloride. So how do we make that N2 group? Well, the first thing we're going to do is take the nitrite, react that with HCl, we're actually going to react it twice with HCl so that we can eventually lose water. And now we can push off water by using one of the lone pairs on O to make a third bond between N and O. And this cation here is resonance stabilized, right? We could draw arrows onto the oxygen, and I can't draw it next to it, so I'll draw it above. So there's my two resonance structures, and this is called a nitrosonium ion. And as you might guess, it is a great electrophile. All right, so I'm going to take my nitrosonium ion, and I'm going to react it with aniline on the next slide. So there's my nitrosonium ion, and if you remember, we are still under acidic conditions, so I still have HCl if I need it. The first step is going to be creation of the NN single bond. And there I would have a cation on my original aniline nitrogen now. I've made this new bond, and I have the NO group right here. My goal is going to be to protonate this oxygen enough so that I can eventually lose water, creating multiple bonds between the two ends. So let's go ahead and do a proton transfer and get rid of this extra hydrogen. Whenever we're in HCl, there's always going to be some water around, so I'm going to use that to proton transfer. I'm going to start abbreviating my phenyl ring just to make things a little more compact here. I got HCl. I'm going to protonate the O. And then I'm going to basically remove the extra hydrogen on the first nitrogen. I'm going to use water again for that. You can see that 3-arrow push. I'm creating a NN pi bond. I'm removing the pi bond between the N and the O, and I'm relieving the cation on the oxygen here. So now I have a pi bond between the two ends, and I have an OH here. And you can see that if I can create water once more, again with more HCl, I can eventually lose that water, form my NN triple bond, and I have my Aryldiazonium now. So I'm going to draw the phenyl ring again. Here's the triple bond that I just formed. There is a cation on this first nitrogen. I did form water, and of course the counter ion probably is a chloride here, and we're going to say that an easier way to draw this is like that. So we're going to use that on the next page to do some substitution reactions, because now we have this great leaving group, nitrogen gas. It's not going to leave by itself, because that would put a plus charge right on that carbon, and we know that that's not going to be very favorable. But you could imagine attacking the ring with an electrophile and eventually losing N2 gas. Let's compare that to maybe an aliphatic diazonium cation, which we could make as well if we had a NH2 group on just a standard alkyl chain. This actually is reasonably prone to losing N2 gas, to making, this arrow should be one away, to losing N2 gas and making this cation. And so it's actually kind of hard to isolate these. They can lose N2 gas explosively because that's, again, liberating a gas. And then we have this really reactive cation that's formed. And so we really don't see aliphatic diazoniums very much at all. So I'm just going to put a cross here. The book does mention them a little bit, but they're really not synthetically useful because it's hard to maintain this diazonium here until we're ready to react it with something. Oftentimes it just reacts on its own, decomposes. So we're going to focus on the Aryldiazoniums on the next slide. So we can do what's called the Sandmeyer reaction. Which basically uses copper salts to install different groups. And I'm just going to call that X. So let's look at our Aryldiazonium. And if we react it with copper bromide, we can install a bromide. Now, that's not all that exciting to us because we learned way back in the aromatic substitution chapter how to make bromobenzene without going through this highly reactive intermediate. So we could also install chloride that way. We could install copper iodide, helps us install iodine, and that's maybe a little more useful than bromine or chlorine. We didn't really learn a way to install iodine in an EAS reaction, so this is a bit more useful. And probably the most useful is copper cyanide installs the CN group on the ring. There's really not another way to do that. So this one, I think, is a very new type of intermediate or product. It's very useful in that we can then derivatize the cyanide a little bit more. One thing we could do, of course, is just to hydrolyze with acid and water to produce benzoic acid. Now, we know other ways to make benzoic acid, but this would be one method that's available to us. Other options, which don't involve copper salts, I'm going to use the same Aryldiazonium, would be the installation of a fluoride, which also is a new reaction. HbF4 basically installs fluoride in place of the N2. We could actually install an OH group using water and heat. And I think this is a key reaction because it's one of the few ways we know of to install OH. And remember, all of this stemmed from having an NH2 group in this location, and the NH2 comes from a nitro group. So now, if we have a nitro group in a position on the ring, we can turn that into a bromine, iodine, cyanide, carboxylic acid, fluoride, OH, and also, interestingly, H3PO2, hypophosphorus acid, can remove the N2 altogether, leaving us with H. So this is interesting too, because we can start with a nitro group, use its directing effects as a meta-director, change it to an NH2 group, an amine, use that meta-directing effects as an ortho-para-director, change it to the Aryldiazonium salt, and eventually remove it altogether. So that's pretty cool. Let's look at what we might be able to do with that. Imagine if we had benzene, we turned it into nitrobenzene, reduce that to aniline, and now we can react aniline with, sorry, I want to use chlorine in this case. We could react it with chlorine 3 times. We know that aniline is highly activated. It's going to add orthopara. We could add 3 chlorines in the orthopara positions. Then we can change, sorry, that should be NaNO2. Then we could change to the Aryldiazonium. With our 3 chlorines. And we could hit it with H3PO2. The N2 group goes away. We've got 3 chlorines all meta to each other. How do you make this without the Aryldiazonium? I don't know. The chlorines are all orthopara directors. There's really no way to put a chlorine on and then add 2 more chlorines meta to that chlorine. So this technique can allow us to make some pretty interesting molecules that we might not otherwise be able to make. Let's look at a couple synthetic examples of this Aryldiazonium process. Imagine our goal was to take benzene and turn it into this tri-substituted aromatic ring with 3 different functional groups. And that should be an I up there. It's not very well drawn. Let's make it a better looking I. So we have an iodine, a chlorine, and a ketone on this ring. So how do we make this? This is a meta-director. It's not going to put the I or the chlorine in the right spot. The I is an orthopara director. The chlorine is an orthopara director. But remember that you can't, it's very difficult to put Friedel-Crafts acylation on when we have a sort of moderately deactivated ring, like we might if we had the iodine and the chlorine on. Also, we can't just use I2 and AlI3. We haven't learned that that works. So probably the best way to get the iodine on there is via copper iodide and the Aryldiazonium. We know that the Aryldiazonium comes from an NH2 group in that position. And now that we have this powerful orthopara director, most likely that's how we got the ketone on the ring. Remember that NH2 comes from NO2, so if there was an NO2 right here, maybe we could add the chlorine meta to that NO2, then change it to NH2 and add the ketone. So I think we probably add the ketone in this step here. We've got the metachlorine, and of course we can reduce with iron NHCl. And I can add the chlorine to nitrobenzene. And I can certainly make nitrobenzene from HNO3, H2SO4. So we've got several steps here, but we put the nitro on first so that we can put the chlorine meta to the nitro. Then we reduce the nitro to the orthopara directing NH2 group, and that can add a ketone in the the para position relative to the NH2. Then we can change the NH2 into the Aryldiazonium salt that can be displaced by iodide to give us our desired product. One more example. What if we wish to take benzene and turn it into meta-diethyl benzene? Both of these are orthopara directors, so there's no way to put one on and then get the other one on in the meta position. So we need to have some sort of directing group that puts these on in this orientation, and then we remove, probably with an Aryldiazonium type reduction. So I think that if we had this situation, I'm trying to get to the NH2 group here, because that is a powerful ortho-para director. And now you can see how those ethyl groups are ortho-para to the NH2. So it might be challenging to do two equivalents here, but let's give it a shot. And then, of course, NH2 comes from, as we saw on the previous slide, HNO3, H2SO4, the nitro. Follow that by zinc NHCl or iron NHCl. We can reduce that to the NH2. That can be doubly alkylated, and then changed into the diazonium. And then, of course, how do we remove the N2, replace it with an H? We use hypophosphorus acid, H3PO2. We'll basically put an H in this position. So we can use the Aryldiazonium to substitute some other functional group, as we saw in the previous slide, or in this case we can use it just to get rid of an NH2 group that served its purpose as a directing group, getting these groups into an unusual meta arrangement. Then we remove it altogether, replacing it with H.